everyone? Yeah? Okay, so I'll start with an example. One thing that I have noticed in all my lectures is people want examples. Yeah? So I'll start with two examples. You can think of these as like, running examples whenever I present algorithms or other ideas, keep these as running examples. Okay? So if students want examples, what do students not want? Proofs. Okay, so there won't be proofs in the 3 lectures that I'm going to do, but the constant refrain that I get is proofs are boring. But in a full-fledged RL course, I make a point that all the algorithms grow out of these proofs. Proofs are not like, okay, there exists a proof and you can look at it or you can ignore it. Inside the proof is a construction for an algorithm. That's how the RL proofs are at least. But I can't do it in these 3 short lectures, but wait for a course. Anyway, the very first example. Okay, a note, okay, so I need to push this down. The textbook resources, I'm going to use the popular ones. Of course, I have a web page, so everyone knows my name. So Google, and there's a website called CS6700 in my website. There a lot of resources are listed. The other popular books are by the book that sets cyclists and Birdsey. Anyone knows the title? Yes? Introduction to Probability. No, we are not doing that course. Yeah. Any other book they wrote? Yeah? No, that's Bishop. That's next Monday. Yeah, next Monday, CS 5691. That's my course. Yeah. Anyway, I moved away from Bishop. I don't like Bishop's book. You can tell Bishop that. Yeah. Yeah. No? Okay, good. It's good because it's good. I don't know if I can use this word. I can probably bullshit and people won't get because this is a subject that nobody seems to know here at least. At least they are pretending. Nobody knows this book. This is a very old book. The other book, which is the most popular RL book, who is the first author? Barta or Sutton? Sutton, okay. So they have a new edition which I have not read. What's the title of the book? Maybe Intro to RL. Okay. And the other books for MDPs are by Birdsey. He has 2 books, Dynamic Programming and Optimal Control, Volume 1 and 2. Okay, these are 2 books, 700 or 600 pages each. Okay, so you can get through all of this, and if you're still alive, then we can do some work together. Yeah. Anyway, so the example. Bulk of my treatment is based on the Birdsey school. I grew up there. So there will be some math involved. So just gear up for it. Yeah. So you got a bus or a machine. Okay, imagine you have a bus like the MTC one here, and it could be in one of the n states in terms of its quality, like whether running condition and things like that. And imagine one is the best state, it's like a brand new bus, and n is the worst. Okay, so you got a bus or a machine. Bus is a machine, and now at every point the bus is in one of these states. It's either in the brand new condition or the best possible state, or it's somewhere in between, or it's in the worst state where it could only be junked probably. And what could you do? What's the best action in life? When you're faced with a situation, what's the best action? Yeah? Do nothing. That's the best action. So you could do nothing about this bus. Or you could be, could repair the bus. Okay. So do nothing or repair. Yeah. So the thing is that when you repair the bus, okay, you could repair the bus in any of the conditions. So you could repair, see the point is one is the brand new bus, okay. There's no point repairing a brand new bus unless you are, trying something. But in any of the other states, 2 to n, if you repair, after repair the bus goes back to 1, okay. And you're looking at a multi-period setup, okay. You're doing this, imagine you have a bus, you're looking at a horizon like 5 years, okay. And you're trying to operate this bus for 5 years. And then every day or maybe every week you look at the condition of the bus once a week and then you decide to do something, okay. So when I repair, that bus goes to the brand new condition which is state 1 and stays there for that period. So the period here could be 1 week. So every 1 week you take some action, okay, and then that changes the state, okay. So here I'm going to say mission goes to the state 1, okay. Yeah, and obviously the cost of a repair is, say, let's denote it by R. It's going to be expensive to restore a bus to a brand new condition, okay. Other than that, are there any other costs that you can think of? If you do nothing, you still have to bear the operating cost, okay. So let's call this GI, and it's fair to assume that you have to spend less to maintain a new bus compared to maintaining a progressively bad bus. Okay, are these assumptions clear? Any questions? Yeah, right now I'm making that, that would be an interesting homework. So I'll analyze this, go back and make this dependent on the state and try to figure what's the best thing to do. Yeah, we'll try to do this, okay. Yeah. It depends on the state, that's an interesting input, but we are not going to do that, okay. We're going to handle a much simpler situation where, magically there is a band which will just touch the bus and irrespective of the bad situation it is in, you charge some R rupees and convert it into a brand new bus, okay. So what characterizes this problem? How can I describe this problem? I can describe this problem in terms of state transition diagrams. Okay, the state transitions. Okay, so the bus, so for this I need some probability, so I'm going to denote this. Pij is the probability of state okay. And what's a reasonable assumption here? If j less than I. The bus automatically does not become better unless you repair, okay. So this is the case, these are the state transitions, these Pijs are the state transitions for the do nothing part, okay. If you do nothing, with some probability the bus gets worse, okay. It could stay in, like if you imagine the bus was in some state, say pick your favorite number, say 3, okay. It would remain in 3 or go to one of the other states, 4 to n, with certain probabilities, okay. But it cannot get better on its own, okay. It cannot get better, and these are probabilities. But in the other case, the state so the point is here the state transition depends on what? What does it depend on? If I'm in a certain state, if I go on to the next state, what governs the state transition? It depends on the, sorry? No, it depends on your action, whether you do nothing or whether you repair, okay. If you do nothing, then the next state transitions happen in a certain way. And if you do something which is the repair part, then the state transitions happen in some way. So this is at the heart of a Markov decision process. See, the point is, how many of you have seen Markov chains before? Yeah, so there, if you recall, what happens is, you are in some state and you go on to another state using some transition probabilities like this. But there are no actions involved. So you can phrase all of Markov decision process as like controlled Markov chains, where you control the transitions, okay, and that control happens through your actions, okay. So we can look at one of the examples. For action repair, it's easy to see. The system could be in one of these states, n minus 1 dot 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 2 and 1, okay. Let me change the color, okay. And when I do this, okay, and this is a with probability 1 transition. So the point is, irrespective of the state that I am in, okay, irrespective of the state that I am in, if I repair, I am going to surely go to the best possible state. So that's probability 1, okay. Yeah, does anyone get that? So this is a fairly simple transition diagram, okay. Now the other way is like you write down the same states. And then you are going to write, okay, so if you are in state n, then you can't get any worse. So you have a loop like this, p and n, okay. And then from here to here, you have a p n minus 1 n, and so on, okay. And from you can go to 2 with probability p1, 2, and then you can keep on drawing these arrows. Okay, like this, okay. This is p1, n minus 1, and so on, okay. You can draw all these arrows, you can go from here to here also, and dot dot dot. I have not filled the entire thing, but the point is, the important thing to notice is you go progressively worse. There are no back transitions. From 2 you cannot go to 1. That only happens if you repair. In all the other cases it gets worse, and from any of these states it can go up or remain there itself. There are self loops. So the diagram that I have drawn is not fully self-contained, but this is just a illustration of how the things happen. So the important thing is, you got state transitions, you have a state transition diagram, and that depends on what? It depends on the action. So you fix an action and you get a state transition diagram for each action. Okay. So effectively you are looking at 2 state transition diagrams. It's like looking at 2 different Markov chains. Okay, got it? Is everyone clear about this? Okay, look at another example. There's no clock here. How many of you play chess? Okay, the next most dangerous statements. Any addicts? No, only one. Is it on chess.com or leeches or real on the board addiction? Chess.com. Okay, I am on leeches, but I can't say if I am an addict. So that was a prelude to a chess match example. Okay, yeah. Imagine there are just 2 games that you are playing against an opponent. Okay, you play 2 games, best of 2. Okay, and obviously the scoring, I hope everyone knows, if you win you get 1 point, if you lose you get nothing, if you draw you get half a point. And then at the end of it, if the scores are tied, then you play sudden death. Okay, sudden death is like you keep on playing a game again and again until somebody wins. Okay, or somebody, okay, no, yeah, yeah. Is this recorded? Seriously? Yeah. Okay. Now I know why everyone is silent. Yeah, good. So what are the 2 styles of play? You could play timid or you could play bold. Okay, right? In any game you can play timid or you can play bold. And let's say if you play timid, So playing style is timid, then bold. Not even sure if I should have drawn this. Then the two outcomes, if you play timid, do you think you can win? I don't think you can win, but anyway, that's the model that we're going to put. You either draw or lose. And that probability is what's a good color for probability? Okay. Okay. So you could choose two different styles. If you play timid, then with probability PD you win any game. With the complementary probability you lose. And similarly for this. And what would be a reasonable thing to assume between PD and PW? If I have to relate them, PD should be greater than PW. Okay. So when you play a timid style, then you have a better chance of drawing than when you play bold, the chance of winning. Okay. Now you play two games. So we'll try to draw the transition diagram to make things clear. So game 1, you don't have any starting advantage. So your scores could be 0-0. And then after game 1, if I play timid, what happens? What does the score become? Okay. It becomes 0-1. Got it? Is this clear? So I play game 1, and if I adopt a timid approach, then after game 1, with probability PD, I'll be in one of. So these are the states. Whatever I've circled are the states. You start with 0-0, and then these are the states that you could end up with, and these are the corresponding probabilities. Is this clear? Yeah, if someone is not clear, please ask. Now the other option is also easy to write. So wow. Okay, so this is what, but we are not playing. So the point is I am playing over 2 rounds. Okay, in the first round I play something, I end up in a state, and then I have to play again. So at the end of round 1, what are the possible scores? It's 3 of them. Okay, so this is for game 1. Similarly for game 2. Game 2 you could be in 1-0 or 0.5, 0.5 or 0-1. Okay, this is for game 2. And what are the next possible states? It could be 2-0 or 1.5, 0.5 or 1-1 or 0.5, 1.5 or 0.2. Then change color. Okay. And if I play timid, I end up here. Okay. And if I play, with the complementary probability, I'll end up here. Got this? Is everyone clear about what's happening, what I'm writing? Okay, so you can fill the rest of the arrows. Just going to put some arrows. So here, again, so I'm looking at timid play here. Okay, for the bold play, homework. Okay, and like this and like this. Okay, you can fill in the arrows. Okay, here also maybe one. Okay, something like this. Okay, this is what you got. Understand? Now the question is, this is the state transition diagrams. Now what is there to figure in this problem? Or even the earlier problem. Have to figure what's the best way to play or what's the best action to take for the bus part, and that's what we are going to look at. So this is just a prelude. We'll get into the theory and come back to these examples. Is someone not clear about these examples? Yeah? Yeah, what part? Huh. No, the bus is just in one of the states. Okay, the bus is in one of the states and it will transition to one of the next states. Okay, and they'll add up to 1. Imagine there are just 2 states, 3 states, okay, 1, 2, 3, okay, and then the bus is in state 1. Then it can remain in state 1. What is that probability? P11. And it can go to the state 2, which is P12. And it can go to third, which is probably n for me, n equals 3, which is P13. And what do you think these probabilities should satisfy? They should be greater than equal to 0, less than equal to 1, and they should sum to 1. That's all there is to it. At any point, the bus or whatever is in just one of the states, and then there's a distribution saying that the next state is following this distribution. The next state will be 1 with some probability. You can put some numbers, 0.4, 0.4, 0.2. So if the bus is in state number 1, there's a 40% chance that it will remain there. There's another 40% chance that it will go to 2, another 20% chance that it will go to 3. So that's the rule about this. I have not made it precise, but that's what these probabilities mean. Okay, is that clear? And then it goes there, but we don't stop the problem. I'm going to make that precise. I'm going to repeat this for n stages, like 5 years I said. Okay, I go and tomorrow again I look at the state, and then there is, but what I'm going to put is these transition probabilities are time independent, in the sense even tomorrow these probabilities would be the same. If the bus is in state 1, it's like 40% to go to 2 and things like that. Okay, so those are transition probabilities. Here we are looking at the stationary setting where these transition probabilities are not time dependent. Okay, yeah, if they are time dependent, I don't know. Yeah, it's beyond the scope of my, or this course at least. Where is the power button? Yeah, here. Okay, it recognized my face. Okay. So we'll get into the framework. If you have any color suggestions, you can give framework. Okay, so what are the components here you started with? You started with a state space, okay. There are a bunch of states and then there are a bunch of actions, okay. And then there is transition probabilities. What I have written there is, in the examples, I didn't make the action explicit in the transition probability, but it depends. So this is the probability that the next state at any point is j, given that the current state is I and the action that you took is a. There's a camera there. How many of you surely know it's recording something? Anyway. Interesting, everyone is awake. Yeah. Now the important thing about this is, why is it called Markov? Okay, out of all the MS PhD interviews, there was one brave soul who picked reinforcement learning. Okay, I was jobless in these interviews generally, and asked him what is Markov and Markov decision processes. Yeah, and he didn't cry, but yeah. Yeah, but why is it Markov? Yeah, it's an emotional question, but yeah. Why is it Markov? What is the Markov part? What do you think is, when I say Markov chains, why is it Markov chain? Why is it not like some other guy's chains? Yeah. Yeah, so it does not depend. So the point is the next state. When I talk about the next state, oh, here is where I can use my art. Okay. I'm actually an amazing drawing person. Yeah. So can you draw a straight line like this? Actually, a colleague asked me, why are you doing this class? I have an answer now. It didn't strike me then. Anyway, so imagine a time t. So this is k, is it? Okay, imagine this is time t. Yeah. It's too much to erase. Yeah. Okay, we'll make it the time index, because there's a chance that I give these notes out. imagine a time you ended up in state I, and then you're looking at actions. So you could have come to this in multiple ways. Okay, so you could be in variety. So you ended up in state I at this point. You ended up in state I at this point, and you could have visited whatever states before and taken whatever actions. Irrespective of that, the very next state at k plus 1 depends only on this state and the action that you are going to take. That's the Markov part. If the future depends only on the current, I mean, conditioned on the present, the future is independent of the past. Okay, yeah. So I hope you understood that. Okay, so I should not go this far. Okay, so the point is the probability that I end up in a state J at time k plus 1 depends only on the current state and the current action, and it does not depend on the past. But I need to know the current state and action. That's the point. Given the present, it's independent of the past. Okay. Is everyone clear about the Markov property? So this is not the Markov property, this is the controlled Markov property, simply because the actions come into picture. Okay, if you take away the actions, what you have is like a Markov chain. You just have a sequence of states and somebody is taking the actions and you don't have control over that. Here you have control. Okay. The important thing is whenever the state transitions happen, you incur some cost or you get a reward. Now since I am in the Bertseka school, I am going to use costs. Okay. You can turn them into rewards by thinking of cost as some negative reward, things like that. You can wrap your head around that. Now, each time I take a transition, I have a cost. So in the bus example, there's a cost. The cost is what? The cost is simple. The cost is if you do nothing, then you have an operating cost, which is smaller than a repair cost. If you choose to take the repair action, you have a cost of R irrespective of the state. But if you choose to do nothing, depending on the state you are, you will incur some operating cost. Okay. And then given this cost, your job is to minimize this cost, not in one state, but imagine I repeat this for say 100 periods, okay, 100 transitions. I'm looking at a horizon. In this horizon, I keep on adding the cost, and then I want to figure out the sequence of actions to take so that this cost is minimum. That's the framework we are going to get to. I'll make all of that precise. Okay. So each time I incur a state transition, I incur a single stage cost. Okay, and I could make it stage dependent. Okay. Yeah, so last time I taught this course, people were confused with stage and state. States are like this I, J, wherever you are. And stage is like you're doing the bus thing for 5 years. Each week is a stage, and then you do something for a week and you go on to the next stage, which is the next week. And you want to do this over 100 stages. So the problem has a number of stages, okay? The problem is over like say 100 stages. In each stage, the system is in some state and you have to take an action, okay? Don't get confused between stage and state. If you have any recommendation for stage, alternative to stage, you can tell me no. I try to take the best word to confuse people, yeah. No? No recommendations? No, the stage, no cost. I want to refer to that stage, like K is the stage. K plus 1 is a stage. I want to do this over multiple stages. Period. Time. Time is, yeah, time is what? I mean, time, slot. Okay, we'll stick to slot. Okay, we'll do this over multiple slot. No, I'll make this more graphic. Okay. And then given this, what's the next thing to make precise? So we have a Markov decision process. You have the Markov covered, and then there's a decision to take, which are the actions. And then what's the objective? Objective is to, you have the costs also. So objective is to choose actions. So for choosing the sequence of actions, we make something called policy formal. Okay. A policy, the most gory color, no, there's no red. Policy. Okay, you're doing this over n slots. Okay, n slots. Okay, and so in each slot you need to specify how you choose actions. Okay, and those are those functions. So these are functions. So you have n slots at the beginning. This function tells you what action to take given a particular state. And then mu1 would tell me what action to take given in a particular state. And so on, I have all these functions. And this whole sequence of functions is my policy. Okay, see the point is, in a chess match, for example, a policy is like, if you take the chess example, in a chess example, the policy cannot just tell that if I'm 1-0, I'll just play a timid strategy. That's not a fully specified policy. The policy has to tell in the second stage, in the second slot, if I'm in 1-0, what I should do. If I'm here, what I should do. If I'm here, what I should do. So for each of these states, it has to recommend an action. Okay, so that's the mu0, mu1, mu2 up till. So here the number of slots were 2. Okay, but you could have any number n of slots, and then you have to specify all these functions. So that's a policy. Do you understand? Is this clear? Sorry? Policy and actions are not the same. So the point is, policy is a sequence of functions. In the first, for example, mu0 is what I would do in the chess game in the first game. In game 1, in a particular state, mu0 would tell me whether I should play timid or bold, given the state, whether it's 0-0, 1-0, things like that. Okay, the action would be timid or bold, but a policy specifies everything. Okay, it's like saying that if I'm in a certain state, what action I will take. And I have to tell this over all the slots. So the policy is over multiple slots, and in each slot over multiple states. Okay. Now we are going to look at additive things. So here mu I is a mapping from state space to action space. Okay, this is the state space. This is the action space. So if I pass a state, mu I is a function. If you give a state, it is going to throw out an action. All right, and it has to be full. It cannot be like incomplete. Yeah. Now, given this, we have a performance metric next, which is in some other color. The performance metric is, so policy pi, j pi, and imagine I'm in a start state. Okay. Yeah, for any given start state, S0 is the expectation of, there is a terminal cost which I didn't introduce, but you can add that, plus summation equals 0 to n minus 1 gk of k of sk comma sk plus 1. Okay, and this I call the terminal cost. You could throw in a terminal cost. At the end of all this, like in the bus example, at the end of 5 years, you would have some cost. You don't have any action to take, but you would have some cost in, say, junking the bus or doing something to that bus. Yeah, okay. So that's the terminal cost. There's no actions there. But in each slot, depending on which state you are in and what action you take and the next state, based on this, you incur a single slot cost. And then you sum all these single slot costs, and then in expectation, this is what you get. Now, why is there an expectation there? Where is the randomness coming in? State transitions, because the next state is not deterministic. Okay. So if you are in a certain state S0, then S1 itself is random. Okay, but it's like it follows the Markov property for sure, and so on. So this expectation is over the sample paths you can think of, S0, S1, S2, and so on until, and also the cost depends on your action. Okay, that's the pi dependence. The reason why this performance metric depends on pi is because you're going to choose actions according to your policy, and that's going to tell you how much single slot cost you get, and that's why this is policy dependent, and there's an expectation because there's a Markov chain underlying all this. Yeah. Yeah, put all of that in the state. Yeah. If it depends on the last 10 days, cover all of those last 10 days variables and put it in the state. Just blow up the state. Yeah. It's still okay. I mean, yeah, if it is not Markov, I mean, yeah, so Bellman is. No, I'm just saying if it is previous 3 states, put all of that in a vector and call it your current state. Okay, think about it, yeah. Oh, this guy can't. Stupid thing. Okay. Stupid thing, it didn't recognize my face. Okay, so the point is, you want to find, the goal is to find pi star, that j pi star of any start state is the best policy. Okay, so that's the goal. So you have a total cost objective. So you are just summing the cost over n slots. That's the horizon, learning whatever, optimization horizon. And you want to find a policy that minimizes your cost. All of this is framed as cost. Is this goal clear to everyone? Yeah? Okay, so the thing is, now we'll go about and try to bring in a very popular idea called dynamic programming. It's a general principle for solving this problem. Okay. Imagine somebody gave you pi star. Okay, imagine somebody told you, yeah. No, you can start in any state. In the bus case, you started with a brand new bus. But if the initial state is like you became the mayor tomorrow, then all the buses are in some, yeah. Is this recorded for sure? Yeah, okay. No, but it depends on where you start. Like, okay, think of an investment thing. If I am like a professor now, if I have a few lakhs, maybe almost a crore, I don't know how much I have, but yeah. Then my investment strategy, I'll go to a firm, but if I'm just starting out, then things like that. Or if I'm an Ambani, yeah, know how much money I have, I go to an investment firm and they'll choose to do some buy and sell, and that will change. So that initial wealth is what matters, initial wealth, okay? Whether you were born with something or you make your own way. Surely recorded, he's looking at me, yeah. Okay, so the thing I was trying to tell was, it's going to be put out on the web somewhere, yeah. Yeah, optimality principle. Okay, so the point is, imagine somebody solved this problem for you. Somebody solved this problem. Somebody found that pi star, and he or she gave you this pi star. Okay, then what can you infer from this? So the point I want to make is, you have a n slot problem. Okay, imagine you have an n slot problem, and for each slot you have figured out what is the optimum part of the policy. Okay. Now if I look at a particular tail problem, I'm going to write the tail problem. So tail subproblem is very much like the original problem, but I'm going to do minimum, I'll call this pi superscript I. This is, I'm going to look at only the tail of this starting in stage I. Okay. I'm going to look at stage I, okay, and then go up to the end. Okay, not from the first slot, not stage, slot. Okay, I'm going to look at ith slot and go up to, there may be compiler errors each time I say stage. Yeah, so I'm going to look at the n minus I slot problem, which is expectation. Why did this change? Again, the same thing, that the terminal cost has not changed. But then when you look at this summation, I am starting from the ith thing. Okay. I equal to n minus 1. K of sk. Okay, do you recognize the important thing? So I am starting in, I'm not going from the first slot, but I'm starting from the ith slot. Now what do you think will be the optimal policy for this? I mean, somebody has given you pi star already. Any guesses? I mean, can I infer something from pi star to solve this problem that I have put, tail sub problem? I'm looking at, see, I have like slots 1 to 100. Okay, I have slots 1 to 100. I have to take an action in each of these slots. And now instead of starting from slot number 1, I'm going to cut half of that. And I'm going to start from slot number 50 and go up to 100. Now, if somebody says that for going from slot number 1 to 100, this is the optimal way to choose actions, then for slot 50 to 100, what should I do? Yeah, they just extract the tail part of that. Just extract the tail part of that pi star, and that should be optimal. Now, what's the most intuitive justification for that if it is not optimal? If there is some part which is, okay, let me make that precise. Okay, claim without proof because proofs are boring. For this tail subproblem, okay. So this is an I hope it's clear, yeah. So for the tail subproblem, this is the best, this is the optimal policy where I have just extracted this from the original optimal policy pi star. Now if this were not optimal, then what would be an intuitive way to argue? I'm not going to do the proof, but suppose this is not optimal, but if you can find some other policy which is optimal for the tail problem, then I can take that and patch it into pi star and get a better j pi. Okay? That just contradicts the fact that pi star is optimal. Do you understand this? That's exactly what is done inside the proof, even though like each line of the proof will have like 40 symbols. That's just one idea. That's very simple. But it's good to work in RL because you can write lengthy proofs and yeah, you can, okay, whatever, yeah. It's still recorded, right? Yeah. Now this already leads to now this is the optimality principle. So now if I want to turn this into an algorithm, what should I do? Now I want to solve the problem. I want to solve this problem. I want to solve this original problem which is exactly at the top of that board. I can't jump there. Okay. Now if I want to solve that problem using this tail idea, what would be a easy way to go about this? Think about this. There's no clock here. Is that by design? Anyway, any ideas? Yeah, solve. Start at the end. Start at the end. Solve the final slot problem. Then solve the final 2 slots problem. If you solve the final 2 slots problem, you will get the optimal policy for those tail subproblem. Use that to solve back, and come up to the first. It's easier to solve it in reverse. Why is it easier? Because if you start from the beginning, then you will have to look at an exponential number of actions. Whereas if you start from the end, you are going to use whatever is in that tail. You figured whatever, that's what you're going to use. Okay. So I'm going to write the dynamic programming algorithm for this. Was the best, this is a page boundary. What I figured. Yeah, this is a page boundary, that's why this block has come here. Now when I release this, I'll make this PDF available. Okay, so there's a page boundary there, I've not seen it. That's the reason why I'm doing the DP algorithm on the next page. And this was student feedback from my last course. The art is my own contribution. Yeah. Dynamic programming algorithm. Okay. So the idea is solve tails of problems starting at the end. Okay. I'll write that. Solve tails of problems and progress backwards. Okay. That's not a loaded statement. So the algorithm. I need to draw a block and then cut out the filling maybe. Style. Oh, what is this doing? Okay, I don't know how to do this. Why is this shaky? Forget this. I thought this should be okay. I can draw a box and I think I can write, but why is this guy not allowing me to do that at all? Anyway, TP algorithm. Okay, in the final slot, there are no actions, okay? There are no actions, so you just set it to the terminal cost, okay? And then you solve tails of problems, so you start with for k equals 0, 1 up till n minus 1, okay? J of sk equals out of space. Plus jk plus 1 now if there are no questions, I'll just go on, okay? That's the best strategy actually. Okay, so just I've learned a new word for teaching. So internalize this algorithm. The word is internalize. Yeah. Don't give feedback for this. There's no TCF, I guess, for this. Anyone from IITM? Yeah. Don't mail me your feedback. Yeah. You can write it on a blog maybe. Yeah. It's okay. Anonymize it. So the important thing to recognize is here I'm optimizing over what? So in this, I'm choosing only one action. Okay. So when I'm looking at this, imagine I'm doing this for n minus 1. Okay. So the point is, I've figured, okay, let's make this more abstract. I've figured this. So here in this, I've figured this already. I've solved jk plus 1. See, I've figured this. So if you are looking at a tails of problem over say 2 slots, if you have done that and you're coming back and solving a 3 slot problem, then you're going to use whatever you have figured for the 2 slot problem in the tail. Okay, that's the jk plus 1. Okay, so figure that part of the tail. Okay, and then once you have figured this, all you have to optimize is the action to take in that particular slot. And then for the future, from there on, you're going to use jk plus 1. Okay, and this jk plus 1 is already figured because you started from the end. Okay, All right, and so you are trying to figure what's the best AK for every given state. And this Sk plus 1 is what is random. Okay, if you take action AK, then you can go to a bunch of next states. All right, so you need to take an expectation over the next state. I hope you have internalized it. Questions? Face ID. Yeah. Questions? I'll give maybe a few seconds for people to think about it. Any questions about this? I'll try to apply this. I'm not going to show that this is optimal. This is going to find the optimal whatever pi star. If you keep running this algorithm, start at the end and come back to the beginning, whatever you get in J0 is actually J star. I mean J pi star. Okay. Yeah? Is this? Oh yeah. Okay. Is this clear? We'll just apply this to the two examples that we saw. Yeah? But is someone unclear about the algorithm itself? Is everyone clear about how to implement this algorithm? Yeah? Next thing is, okay, just for simplicity, assume there's no terminal cost, okay, just to make everything simple. Suppose your okay, so then the algorithm becomes Jn of any state. I'm going to index, so the states, recall the states 1 to n. Okay. And the terminal cost I'm saying is 0. So the first step I'm going to set j as 0. Okay. Jn of I equals 0. Yeah. And then I'm going to do jk of I is going to be, it has to be a minimum of, see this is the minimum of the, how many actions are there in any state? 2. Okay. So I'll have two expressions to take minimum over. Okay. In the first case, if I repair, what's the cost that I incur? R. Then where do I go? 1. Okay. And then my next state is, if you look at this, I go to state 1. So when I repair, immediately I transition to state 1. And I'm there for 1 slot. So the maintenance is G of 1. Okay. R plus G of 1. That's the cost. And the next state is 1 at the end of that slot. So it's JK plus 1 of 1. You understand? There, you see the DP algorithm, the recursion there. This is super simple because there's just one next state in this case. In the other case, what about the other case? Operating cost, if I am in state I, then the operating cost is G of I. And then, what is the next state? Jk plus of, not J, it won't be I, it could go to one of the next states with a certain probability. So there will be a summation here. Okay, summation over J. Wow, my font is bad. Okay, I'll write this on the next line. If I go to state J, sorry, not Pij. Then I write it as Gk plus 1 of J. Okay. What are the possible values of J? Greater than or equal to I. Okay, that's all. Okay. Got this? Is everyone clear about this? Yeah? You can revisit the chess example. I mean, just to make things simple, what matters is like I don't have to store. Imagine I'm doing this over n slots. Okay, I'm playing n games. Okay, the slot is a game here. I'm playing n games. So do I have to store whether the score is whether I won 6 games and he won 8, or can I store just one number? If I have to store just one number, what do I have to store? The difference of scores. Okay, if I store the difference of scores, if it is 0, 1, I'll just store minus 1. If it is 0, 2, I'll store minus 2. If it is 0, 10, I'll just go home. Okay, yeah, things like that. It's not worth playing, yeah. Okay, so I'm going to say the state is the net score. Okay, which is number of wins minus number of losses. Okay. That's already enough. I don't have to store the exact number. Your strategy is defined by the deficit. Yeah, so it's enough. Or the plus whatever. What's the opposite of deficit? People didn't write GRE. No one asked the antonym of deficit. I wrote GRE, but I don't know. Surplus, yeah, surplus. Yeah, good. That's not even a GRE word, yeah. Okay, so we are doing this over max. The DP algorithm will do, it's like you are trying to win, okay? You're not, so you can do the DP algorithm with rewards and turn all the mean to max, okay? The same logic, okay? So I don't want to turn this into the other side and all. So I just have to take max over 2 actions, okay? Now I could play timid. If I play timid, then with probability, if I play timid with probability PD, what will be the next state? If I play PD, then I get to, if I with probability PD, I draw. Okay, so the next state is going to be, if you're same, because it doesn't change, you drew, the net score is going to be the same. The net score is going to be the same, okay. Each person gets half a point, but yeah, nothing changes in the net score. So JK plus 1 of SK. And with 1 minus PD, where do I go? SK minus 1, that's all. Okay, and similarly write it down for bold. For bold, with PW I win, so JK plus 1 would be SK plus 1, not SK plus 1 like this. Yeah. SK. Yeah, please don't confuse this. SK minus 1 is like whatever net score and then subtract 1. It's not like the previous state or something. Okay, don't get confused. So that SK plus 1, that plus 1 is a, K is a subscript, plus 1 is not. Yeah. Plus 1 minus PW into this is all the DP algorithm is. Now intuitively, if this is the situation, what would be, what do you think, as a human, what do you think is the optimal strategy for such a problem? If you want to win this game, yeah. Win this match, okay, match, which is over multiple games. Like in terms of net score, you have to just look at the net score, okay. If you're leading, play timid. And otherwise, play bold. Okay, so we can use this DP algorithm and all this formalism to actually show that that's optimal. Okay, we can establish using this framework that play timid when leading and play bold otherwise is the optimal policy. Okay, we can show that. We'll just, I don't know how much time I have because I'm doing finite horizon MDPs forever. Yeah, I think I can do this chess example. How many of you want to continue this example and how many of you are asking for more algorithms and theory? How many of you want this example to be continued? At least, good. Yeah. Yeah, I want to continue this, so let's see. So the point is, when will I play bold? When the expression for that is better than the expression for the other one. Okay. So play bold if, you can just rearrange and what you will get is I hope this is correct. You can check. So when I write, there may be an embarrassing number of errors. And if you just follow it blindly, then I am not responsible. So please check whatever I write. Yeah. Okay. So that's really the condition. You just write it down, collect terms related to PW on one side, PD on the other side, take the ratio, that's what you will get. Okay. So you just want that number, whatever for bold, to be greater than the corresponding one for the timid play. Okay. But this is too abstract, so let's try something else. So now what would be the initial condition? See, this is just the recursion part, okay? But you have to start at the end, and there is sudden death there. Okay, do you remember the sudden death there? And then you have to come backwards. So in the end, so Jn of Sn. Now if Sn is greater than 0, then what has happened? You have 1, that's all. Okay, so put 1. And if Sn is less than 0, then it is 0. And if Sn equals 0, then your chances of winning or losing will come down to, if you keep drawing, then there's nothing, then its score does not change. Okay. Okay, so the point I want to make is, in sudden death, is there something that you have to figure out for that style of play? Is it even worth playing timid there? In sudden death, whoever wins first wins the match. Okay. So, so the point is, you just play bold there, because if you play timid, you have 0 chance of winning according to the game here. Okay, according to the way we have formulated it. When you play timid, you can either draw or lose, but you cannot win. Okay, but if you want to win the match in the sudden death phase, you just have to play bold. I think that much is obvious. Okay, so your chances, whatever comes down to this, please think about this. But this is where I start. Okay, I figured the final stage, final slot, and now I have to backtrack. Okay, I have to backtrack, and that's what I am going to do now. Okay. So I'm going to solve Jn minus 1 now. I've figured Jn. I'm going to solve for Jn minus 1 using this equation, but just bunch of intuitive arguments. So Sn minus 1 could be greater than 1, equal to 1, could be 0, could be minus 1, and I don't care about the other. Okay. This is probably straight. Okay. In this first row, I think everything is simple. See, Sn minus 1 is greater than 1. So then you have won the game. Okay. Yeah. If it is greater than 1, it means that the difference is at least 2. Okay. So even if you lose the last one, it does not matter, you have won it. You understand this? You are starting the n minus 1th stage, which is 2 games to go, with a +2 score. Okay, with a +2 score, then even if you lose one more, I mean, yeah, whatever. Okay. It's hard to say, so it does not matter. This is not the interesting bit. Okay, if you have already won hands down with just one more game to go, if you have already, not 2 games, with just one more game to go, if you have won the match, then it does not matter. Okay. Now, if you have a deficit of 1, okay, which is you are on the +1 side and you have one more game to go. Understand? You have one more game to go and you are at a +1, okay. Then what you have to do is, I can erase this part. Oh, this erases the whole thing. Okay. I want to do maximum of, see what could happen, I could, with probability PD, where will I go? If I draw, then I will go to Jn of 1. So it's just PD plus, the point is PD into 1, that is, the next state is Jn of Sn. If you invoke, it's just 1. Okay. Do you understand? Because I'll go to a +1 state, it just means that Jn is 1. Okay. But if I don't, so this is for timid play. Okay. If I don't, I mean if I lose, then the scores are even. Okay. Okay. And then the next state is PW. This is for timid play. Okay. In the n minus 1th stage, this is for timid play. All right. And similarly for bold play, what will happen? PW. With PW, I win. Okay. With 1 minus PW into PW. Now, can you just use the fact that PD greater than PW and figure which is the best strategy? So you want to take the max between these two. You take the maximum between these two, whichever is better. Okay. Tell me which is better. Did someone get timid is better? Did anyone try? I'm not going to simplify, it's a very simple expression. Yeah? Timid, yeah. So the fact that you use is PD greater than PW. Okay, please use the fact, then write out the entire term 1 PW plus whatever, yeah, and then you'll be able to see it easily. Now the first part of the conclusion is already clear. See, the point is, what was our intuitive thing? When you are leading, what's the optimum thing to do? Timid play. Okay, this is for the, and then when you are lagging, you can figure this. Okay. Let's try to fill a couple more rows. When the scores are tied, okay. When the scores are tied, I'm not going to write out the max, but what do you think is the best? Bold. Now these are things I'm not going to check the details. I'm not going to show the details. You can check this. I'm writing out the actual cost also. You can infer this, PW square. again bold play is best. And this is something you can, and then the last bit is nothing, less than -1, 0. Just leave it, yeah. Okay, so this confirms our intuition. You can extend this to n slots. I just did 1 slot. Okay, you can continue this and infer that, even for a n slot game, if you are leading, play timid, and otherwise just play bold. That's the optimum under these assumptions. Okay, yeah. Any questions about this example? Anyway, so I can show one more thing. Actually, this is the most interesting conclusion. Okay, so that for the 2-game match, what you want to figure is this, correct? I'm starting at 0, okay? Okay, I'm starting at 0. I have 2 games to go. I want to figure which is the best way to go about this. Okay. And then this is going to be maximum between 2 options. If you draw, where do you go? You go to 0, and then Jn minus 1 of 0 is Pw, okay? And if I lose, then I go to -1, and that is Pw square. That's the next state, okay? See, the point is I'm looking at Jn minus 2, and then when I put in this PD, or when I'm when I take a state transition, the next slot would be Jn minus 1, okay? So this would be Pw square, okay? All right, so this is for timid play. This is probably too fast, but I'm trying to make this. So the point is, I have 2 games to go, okay? That's Jn minus 2, okay? And I'm going to take one transition, and I'm looking at the timid side of things. When I play timid, and with probability PD, I draw. So the net score will remain the same, so I'll end up in the next state as 0. And Jn minus 1 of 0, we just figured that it is Pw, so it's PD into Pw. Okay, similarly the other part. Okay, and then the other part is similarly Pw into. So if I win, where do I go? I go to +1, and that is that expression. Okay, PD into that top thing. Okay, so that's exactly what I'm going to write. P. Okay, but I could lose. Okay, and if I lose, it's going to Pw square. It's Pw square because I'm in score 0. Okay, and if I lose, I end up in -1, and I take out Pw square. And this is for bold. Now, this max, you have to go back and check. Okay, is actually the bold part. You can check. It's not too difficult. Maybe there may be some minor condition on PD and PW, but I think under reasonable condition you can work out that the second one is best. Okay. We just says that when you have 2 more games to go, and if you are not leading, then play bold. That's exactly what I have just shown. Okay, the maximum is you have to compare those 2 expressions, write it out, and then it should be easy to infer. Yeah. All right. Any questions? See, this is where I'm going to end finite horizon MDPs and move on to something called discounted MDPs. If you have any questions about finite horizon MDPs, this is the time to ask. Any questions? No. This or the above? Yeah. No, the thing is, when you repair, it goes there, and then it stays there for one slot. No, so the point is, if you repair, it becomes a brand new bus. Okay, and then for that one, like think of weeks, like for that week, you have to still maintain a brand new bus. Yeah. Yeah. It's a modeling assumption. If you think your brand new bus requires no maintenance, then you can say that it's 0 or something like that. Yeah. The other assumption is like R is much greater than G of 1 to G of, or R is much greater than G of n maybe. Yeah. Like it's costlier to repair than operate a bad bus. Okay. Yeah, some other diagram now. Any questions? I'll just introduce the infinite horizon MDPs and then we'll break for coffee. Yeah, so the thing is, there will be an assignment that will be circulated, okay. You have, that's a take-home assignment. It contains both theory and simulation exercises. You have to write it up and do some simulations and submit the report and send it to my TAs, okay. Yeah. We'll just email because I didn't get time to put it on my website, yeah. We'll email that assignment. I think the organizer will circulate. I don't have any email IDs of students, yeah. And if you have questions about that assignment, you can contact the TAs and then me, okay, you can contact me. Yeah, you can come to my office, but you have to book an appointment because there's a chance that I'm not around, yeah. Okay. So the difference between previous and this is we have an infinite number of slots, okay. Just keep the problem going on and on forever, okay. And then we add a discount factor, and so the rest of the pieces are the same. You have a bunch of states, and in each state you can take a bunch of actions, and then each time you transition there is a cost. All of those remain, only the performance objective changes, okay. So let's call this, you have a bunch of states. N could be large. Just for simplicity, I am going to write it as 1 to n. N could be large. I mean, you could have a countable number of states also, countably infinite number of states. And then you have some actions. And then you have a policy. You have an infinite number of slots. Okay. So you have to tell what you have to do in each slot. Okay. Where mu I is as before, mapping from states to actions. And then what we call is a stationary policy. A stationary policy is something that does the same thing in each slot. Okay. It's not going to change its function. Okay. Irrespective of the slot number, yeah, irrespective of the slot number, if you are in a certain state, if the MDP is in a certain state, you choose the same action. Okay. Whereas the other one is, time dependent. It's not stationary. Okay. And it's enough, we just look at stationary policies in this discounted MDPs. So you define J pi of any start state is the expectation. And there's no terminal cost because it does not end. It's like just at the end. Okay. And the number of slots are infinite. and then for each slot you have a cost. And this pi and mu we'll use interchangeably. If it's a stationary policy, it's just you taking actions according to one function. We'll just use pi to denote that. Okay, and sk plus 1. Okay, all right. Now I ran out of space. Given s not equals I. Okay, so you can keep adding this cost forever, but just to make things manageable mathematically, and also for some practical motivation, you throw in something called a discount. The idea, so this is where I can change the color. I can even do some shading. Okay. The others are simple. G is the single slot cost as before. Okay. Pi is the policy, and I is the start state. Okay. All right. Yeah, previously we just added these costs until like say n slots. We are going forever, and we are throwing in a discount factor. Now, now the thing is, discount factor can be easily financially motivated. It's like, after a year, if you get a lakh, it's not worth lakh in your pocket or in a bank or in your wallet, Amazon, wherever. Now, it's only worth 90,000 now. You can think of it like that. Okay. So if you get some money in the future, yeah, or if you see some gain in the future, it's not experiencing the same gain today, so you just discount it. Okay, that's the discount part. Okay, so all your future gains could be discounted. All right, and it also makes things manageable because you are, mathematically you are adding, an infinite number of, terms, and that expectation may even exist. Yeah. So if you have alpha less than 1 and if your single slot costs are bounded, then you can assume that, okay, I mean, you can infer that this cost is finite. But we can brush all the mathematical things aside, just stick to this, and we'll try to figure how to find the policy which optimizes this. Yeah? All right? So the goal as before, anyway, I'll give you, I think one of the feedback that I got is like give like 10 seconds break. Like, like to stare at these, yeah, not dream or something, yeah. Yeah. Any questions about this? Now the thing is, there are two other, so this is an infinite horizon cost, okay. You need not do discounted cost, you have two other options. One is called the average cost. See here you're taking the discounted sum of things. I mean, you can take the average also, that's the average cost MDPs, that's an entire, and the third one is called episodic or stochastic shortest path. And the ideas that I introduce here should roughly carry over to the other side of things also, yeah. You need to do a full-fledged course, but I'm going to work with only discounted MDPs for the rest of this tutorial, today and tomorrow. And you could read up Pertsekas for average cost and other things. I can't remember. I don't think Sutton handles average cost, but Sutton has episodic and discounted cost. No, discounted reward. He calls it reward. Yeah. Okay. You can read all of those books. Yeah. Any questions about this? Is everyone clear about the objective here? Clear about the discounted cost part? All right.